You know that specific feeling you get when you walk up to a unit on a cold morning?
Oh, I do.
The driver's just staring at you, coffee hasn't kicked in, the alarm light is flashing that angry amber color, and you pull up the code, and it's just money. Alarm, ZO7, check engine RPM sensor.
Oh, I know that feeling well.
Right now.
It's deceptive.
Yeah.
On the surface, it feels like the most basic entry-level electrical gremlin you could possibly find. It sounds like, hey, grab a 34 wrench, change the sensor, clear the code, and go grab lunch.
Exactly. It feels like a 5-minute fix. But that attitude, that it's just a sensor mindset, is exactly how you end up with a comeback repair.
It is.
And we both know there's nothing worse than a fleet manager screaming down the phone because a load got rejected over a sensor you thought you fixed yesterday.
That's the reality of it. It's never just a sensor, and that's why we're digging into the technical service manual today. Because when you actually look at the logic, Alarm 07 isn't just a dead part notification. It is a communication breakdown. It represents a fundamental disagreement between the engine's physical reality, the pistons moving, and its digital brain.
And if you don't understand the argument they're having, you are just throwing parts at a ghost. So, welcome to the deep dive.
Right.
We are shifting gears, pun intended, into a very specific mode today. We've got the alarm code charts, the circuit descriptions, and the diagnostic flows right in front of us.
But we aren't reading them like a textbook. We're going to approach this conversation like two senior techs standing at the back of the truck, looking at the schematics, trying to figure out why this thing won't run.
Yeah, we want the logic.
We want the logic, not just the swap it out instructions.
That's the plan. We want to decode exactly how the base controller interprets engine speed, why this specific alarm triggers massive emissions failures in modern units, which is a huge deal, and walk through a precise diagnostic path.
And spoiler alert for anyone listening who might be holding a wrench right now, there is a specific physical adjustment, a half-turn rule, that seems to be the difference between a fixed unit and a broken one.
I've seen seasoned guys miss this.
All the time.
I've seen that half-turn rule overlooked so many times. But let's start at the component level. Before we get into failure modes and the diagnostic nightmare, what are we actually dealing with here? What's the anatomy of this sensor?
So physically, we are talking about the flywheel sensor. It's a magnetic proximity sensor.
Okay.
And location matters here. It's homed on the flywheel housing, sitting right above the starter.
Which is a humble spot, but it has the most important view in the house. It's watching the flywheel teeth spin by.
But it's a harsh environment.
Oh yeah, you've got vibration, heat from the block, road grime, everything.
Right. And proximity is the key word. It detects the presence of metal without actually touching it.
So it's an inductive sensor?
Technically, yes. Inside that little stainless steel barrel, there is a coil and a magnet. Every time a steel flywheel tooth passes the face of that sensor, it disturbs the magnetic field.
And that disturbance induces a voltage pulse in the coil.
Exactly.
So it's a generator.
In a tiny microsense, yes. It creates a pulse. The base controller, the brains of the operation, receives these pulses. It counts them up over a set time, does the math, and converts that pulse count into an RPM reading.
So in a perfect world, the engine is spinning, the teeth are blurring past, the sensor is pulsing like a heartbeat, and the computer says, okay, we're doing 1800 RPM, everything is good.
Precisely. Now, looking at the schematic, and this is where I see guys get tripped up, the wiring context is critical.
Okay.
It's a simple two-wire circuit. You'll see them labeled FS101 and FS201.
And for anyone who's used to dealing with standard DC sensors where you have a clear positive, negative, and signal wire, this is different.
Completely different. It is not polarity sensitive. Because it's generating an AC signal, which we'll get to in the diagnostics, it does not matter which way the current flows through the specific loop. It connects back to the interface board on the 36-pin connector, specifically pins 35 and 36. It's a closed loop, effectively generating its own signal.
Okay, so we have a simple setup. 2 wires, 1 magnet, looking at teeth. So how does it go wrong? How does the base controller decide to throw alarm 07? Because you mentioned earlier this is about a disagreement.
This is where the engineering gets fascinating. The alarm logic isn't just, I don't see the sensor. It's smarter than that.
It performs a sanity check.
Exactly. It cross-references the RPM data with other data points to see if the story adds up.
It's playing detective. It's looking at the other witnesses.
It is. There are 3 main conditions that trigger this alarm. Let's look at the first one. I call this the running but blind scenario.
Okay.
The computer looks at the alternator frequency. If that frequency is high, specifically greater than 100 hertz, and the oil pressure input is high,
then the engine has to be running. You cannot have 100 hertz coming off the alternator and high oil pressure if the engine is stopped.
Physics doesn't allow that.
Right.
The engine is roaring. But simultaneously, the RPM sensor is reporting less than 800 RPM.
Ah, I see. So the computer says, hey, the alternator is spinning fast, the oil's pressurized, but this RPM guy is telling me we're barely idling or stopped.
Correct. It's a contradiction. The computer trusts the alternator and oil pressure more than the RPM sensor in this instance. It assumes the RPM sensor is lying. That's trigger number 1.
Which brings us to trigger number 2.
It's similar, but for a sustained low reading. Same preconditions. Alternator is cranking over 100 hertz, oil pressure is high. But in this case, the RPM sensor reads less than 300 RPM for 4 continuous seconds.
4 seconds is a lifetime in engine terms.
It is.
If you have oil pressure and alternator output, it is physically impossible to be at 300 RPM for 4 seconds without the engine stalling out completely.
Exactly. So again, the computer flags the sensor as faulty. It knows that data cannot be real.
And the third one.
The third one is a start failure. During a crank attempt, if the RPM registers less than 40.
Less than 40, that's basically 0.
Right. If the starter is engaged, that flywheel is moving. If the sensor sees nothing, literally less than 40, it sets the code immediately.
Now, I want to pivot to the so what factor, because usually a check alarm like this just means fix me when you can. The unit might keep running in a limp mode, but looking at the notes on Tier 4 engines, this seems different. If I'm working on a newer unit, why does Alarm 07 suddenly become a nightmare?
This is the domino effect. On units equipped with Tier 4 engines, everything is interconnected. If Alarm 07 sets, it automatically triggers a second alarm, alarm code 163.
Which is a mission control failure.
Right, and that stops the truck, or at least it puts you in a severe D-rate.
So a bad speed sensor triggers an emissions failure. That feels unrelated. I can hear the customer now asking why they need an emissions diagnostic for a speed sensor.
It feels unrelated, but think about the chemistry. The emission system, the dosing of urea, the DEF, the regeneration cycles, the exhaust management, it relies entirely on knowing exactly how hard the engine is working. It needs accurate RPM and load data to regulate the exhaust treatment.
Of course, if it doesn't know the RPM, it doesn't know how much exhaust is flowing. It can't dose the DEF correctly.
Exactly. If the RPM data is garbage, the emission system is flying blind. It can't comply with EPA regulations. So the system defaults to fail, throws code 163, and shuts down the party.
So you could have a perfectly healthy emission system, DPF is clean, DEF injector is fine, but because this little proximity sensor is loose or dirty, the whole truck thinks it's polluting the atmosphere.
And that is why we don't just swap parts. We need to diagnose this properly.
Yeah.
I have seen guys replace DPF filters or expensive dosing modules because of code 163 when the real problem was a loose RPM sensor lock nut.
That is an expensive bad day. That's how you lose a customer. So let's get into the fix. We're standing in front of the unit. Alarm 07 is active. What is step 0?
Step 0 is put the wrench down. Do not touch the sensor yet.
The data first approach. I'm a big fan of this.
We need to use WinTrack. We need to download the Service Watch data logger. You want to look at the technician user level data. You need to see exactly what happened at the moment the alarm set.
We're looking for context because the driver might just say, it quit.
It quit tells us nothing. We're looking to validate the triggers we just discussed. Did the alarm trigger during startup? Did it happen while running at high speed? Was the alternator frequency reading correctly in the log?
The data tells the story.
The data will tell you which those 3 trigger conditions actually happened. That narrows your hunt immediately.
Okay, so we've checked the data. Let's say we see the running but blind scenario. High alternator output, 0 RPM. Now we go to physical diagnostics.
Now I pop the hood. And the first test is the AC voltage test.
And this is where people get tripped up. AC voltage, I think 99% of sensors on a truck are DC. Why are we testing for AC here?
It goes back to the anatomy we discussed. It's a magnetic induction sensor. As that metal tooth flies past the magnet in the sensor, it induces a current. That current alternates positive, negative, matching the teeth.
A mini generator.
It is literally a mini generator. It doesn't receive power, it makes power.
So we are looking for sine wave, essentially. What is the target number on the multimeter?
You disconnect the sensor wires, run the engine, assuming it will start, or crank it if it won't, and check across the sensor terminals. You were looking for anything greater than 1.0 VAC, 1 volt.
That seems low.
It's a signal voltage, not a power voltage. If you have more than 1 volt AC, the sensor is generating a pulse. It's talking.
Okay, but what if it's whispering? What if we get like 0.2 volts? or 0?
If the voltage is low less than 1.0 VAC, you have two possibilities. One, the sensor is internally dead, or two, and this is much more common, it's just too far away from the flywheel.
It's nearsighted. The gap is too big.
Basically, the magnetic field is weak. It falls off very fast as you move away from the metal. It needs to be closer to generate that 1 volt.
And this brings us to the most critical part.
This brings us to the most critical part of this entire deep dive. If you take nothing else away from this, take this, the adjustment procedure.
The back out 1/2 turn rule.
It is the golden rule of flywheel sensors. If that voltage is low, you don't toss the sensor. You adjust it. But you have to follow the procedure exactly or you will destroy the sensor.
Walk us through it. Be specific.
Okay, first, turn the unit off. Obviously,
Okay.
Safety first. Loosen the lock nut on the sensor body so the sensor can spin freely in the threads.
Got it.
Now, you turn the sensor in clockwise, threading it towards the flywheel until it physically touches.
You want it to bottom out against a tooth.
Gently.
Yes.
You want 0 gap. Metal on metal. You feel it stop. Now, here is the magic. From that contact point, you back the sensor out counterclockwise, exactly 1/2 turn, 180 degrees.
Not a full turn, not a quarter turn.
1/2 turn. That sets the perfect gap. It's close enough to generate a strong voltage signal, getting you over that 1.0 volt threshold, but far enough away that the flywheel won't grind the face of the sensor off when the engine vibrates.
It's the Goldilocks zone.
Exactly. Then you tighten the lock nut, and you have to hold the sensor body while you tighten the nut so it doesn't spin back in.
And then we retest.
Then you restart the unit and check that AC voltage again. If you did the adjustment properly and you were still getting less than 1.0 VAC, then, and only then, is the sensor confirmed defective.
That logic saves so many parts. I can't tell you how many sensors I've seen replaced that just needed a 1/2 turn adjustment. But let's play devil's advocate.
Oh.
What if the sensor is screaming loud and clear? We test it and we get 2.5 volts AC. The sensor's fine, the adjustment is fine, but the alarm is still active.
Then the sensor is shouting, but the base controller can't hear it.
The problem is in the wiring.
The problem is in the wiring. We need to check the path. Diagnostics Part 3, the wiring hunt. Correct. We are looking for shorts or opens. First, the short check. You disconnect the harness at the base controller and at the sensor, so the wires are floating connected to nothing. You take your fluke meter, set it to ohms, and check FS101 and FS201 for shorts to chassis ground.
Basically is a bare wire touching the frame somewhere.
Exactly. Vibration is the enemy here. We're looking for a rub mark. If you see continuity to ground, you've got a rubbed wire shorting out the signal. You need to find the chafing and fix it.
And if there's no short to ground,
Then we check for continuity. Is the wire broken internally? The easiest way to do this is the loop check.
okay.
You connect FS101 to FS201 down at the sensor end. You just jumper them together with a paper clip or a jumper wire.
Creating a shortcut.
Right. Then you go up to the interface board connector, that J7 plug we mentioned earlier,
Okay.
and you measure the resistance of the whole loop.
That's smart because it tests the connectors too. If there's corrosion in the plug, you'll see it there. What's the pass criteria?
It must be less than 1 ohm. If it's higher than that, or if it reads OL for open loop, you have a break in the wire or a bad pin connection somewhere.
Simple, logical. I like that. It removes the guesswork. So we've checked the voltage, we've done the 1/2 turn adjustment, we've checked the wiring. Is there any final check on the sensor itself? Just to be absolutely sure.
Yes, Diagnostics Part 4. You can check the internal health of the sensor coil with resistance.
Ah,
With the wires disconnected, measure the resistance across the 2 sensor terminals directly on the sensor body.
we're measuring the copper winding inside.
Right. The target range is approximately 250 to 300 ohms.
250 to 300, that's a tight window.
It is. If it's 0, the coil is shorted internally. If it's infinite, the coil is broken. And you should also check each terminal to the metal body of the sensor to ground.
Okay.
There should be no continuity. If the internals are touching the casing, it's trash.
And one final housekeeping note. If we find the problem, fix the wire, or adjust the sensor, does the alarm go away on its own?
No. Alarm 07 is a check alarm. It stays in memory. You must clear it manually once the repair is verified.
Don't forget to take out the trash, essentially.
Exactly. If you don't clear it, the next guy's going to think it's still active.
So let's recap this journey. We started with a flashing light, alarm 07. We learned that the flywheel sensor isn't just a magnet, it's the heartbeat monitor for the engine.
And we learned that the base controller uses a sanity check logic, comparing alternator frequency and oil pressure against RPM to decide if the sensor is lying.
That logic is key.
It's everything.
We also discovered the high stakes for Tier 4 units. That Alarm 07 is the domino that knocks down the emission system, causing Alarm 163.
Which is huge. That knowledge alone saves so much misdiagnosis time. If you see code 163, check your RPM sensor first. Don't go ordering a DPF.
And then the workflow. Step 1, data first with Service Watch. Step 2, AC voltage test, looking for that 1.0 volt. Step 3, the crucial adjustment. Touch the flywheel, back out 1/2 turn.
Don't forget it.
Step 4, verify the wiring loop is less than 1 ohm. Step 5, verify the sensor resistance is 250 to 300 ohms.
If you follow that path, you will find the problem. You won't be guessing. And you won't be the guy swapping parts hoping for a miracle.
It really highlights the difference between a parts changer and a technician. A parts changer sees code 07 and orders a sensor. A technician sees code 07 and grabs the laptop and a multimeter.
That's the goal. We want to solve the problem, not just treat the symptom. And frankly, adjusting that lock net is a lot cheaper and faster than replacing a sensor that wasn't broken in the first place.
And the fleet manager will love you.
They will.
Absolutely. You know, what stands out to me the most in all this, it's that 1/2 turn.
It is the key.
I mean, think about the complexity of a modern diesel engine, the computers, the high-pressure fuel rails, the chemical plants in the exhaust system. It is incredibly high-tech.
Right.
And yet, this massive system can be brought to its knees-failed emissions, alarm codes, downtime, all because a tiny threaded rod was 1 millimeter too far to the left.
It really is wild when you zoom out. We tend to think of mechanical failures as explosions or snapped belts. But in the digital age of engines, a failure is often just a matter of signal integrity. The engine is fine, the computer just thinks it's broken because the whisper coming from that sensor isn't loud enough.
A misunderstanding worth thousands of dollars in downtime.
Precisely.
Well, next time you see Alarm 07, don't roll your eyes. Grab your service watch data, grab your voltmeter, and remember the half-turn rule.
And check your grounds.
Always check your grounds. Thanks for listening to this deep dive into the 07 RPM sensor. Good luck out there in the bay.
Stay safe.